Welcome to this video with an example of analyzing determinate structures. This is one of several videos in a short course on equilibrium posted at terje's Toolbox, a website that contains notes, examples, and algorithms for structural analysis. Please visit the website for more videos and other material relevant for this course. This example is a portal frame with 2 columns and 1 beam. Notice the pin support at the lower left side and the roller support at the lower right side. Those support conditions imply that the frame is statically determinate. We calculate the degree of static indeterminacy in the course on statically indeterminate structures. The general procedure for analyzing statically determinate structures is to start by calculating the reaction forces. The 3 equilibrium equations at our disposal suggests that the vertical reaction force at point D is 4.8 kN. It is an upwards force, meaning the ground underneath is experiencing compression. The horizontal reaction force at point A is 12 kN. It is acting towards the left in order to hold the frame from being pulled to the right by the external load. The vertical reaction force at point A is 4.8 kN. Note that this is a downwards acting force, which implies that the foundation is in tension in order to prevent this column from lifting off the ground due to the load acting on the frame. It is important that we now follow the procedure that we have established for analyzing determinate structures. That means we now aim at the bending moment values at selected locations. It is natural that we aim for the moment value at points A, B, C, and D. At point A and D, the moment is 0 because these are locations with pin and roller supports. The bending moment value at the upper right corner of the frame is obtained by first imagining that we cut the frame here and hold the frame with our hand at the cut. We arbitrarily select to hold the column from C to D in this manner. Holding the other end, for the L-shaped portion from A to B to C would give exactly the same bending moment. Notice here that the portion we are holding is a cantilevered column with uniformly distributed load. We have analyzed such a structure in an earlier video, so we now simply state that the moment value is QL squared over 2. The value is 24 kN. The bending moment at B is calculated in a similar fashion. We cut the frame at point B and hold member AB with our hand at point B. The only force acting perpendicular to this member is the leftwards acting reaction force at point A. The force is 12 kN and the length of the column is 4 meters. As a result, the bending moment at point B is 48 kN. Do you see how the horizontal leftwards acting force at equal to 12 kN gives tension on the right-hand side of the column at point B? If not, hold your plastic ruler vertically to mimic this column, apply the force, and feel with your hand which side is in tension. This is an important exercise that builds intuition and experience with which side is in tension. Remember, we draw all bending moment diagrams on the tension side. Drawing lines between the bending moment values we just found leads to this bending moment diagram. There is only load along member CD, so the line is straight from A to B and from B to C. If you turn your head 90 degrees, then you may see why the parabola goes in this direction. Another approach is to say that the curve of the bending moment diagram for members with distributed load curves like a sail would do in the wind, where the wind is represented by the arrows of the distributed load. This rule is a result of the fact that we are drawing the bending moment diagram on the tension side of the members. Now that we have the bending moment diagram, we are ready to address the shear force diagram. Members AB and BC are easy. These members do not have load along them, so we simply use the fact that the shear force is change in moment along the member, divided by the length of the member. That leads to 12 kN shear force in column AB and 4.8 kN shear force in beam BC. The shear in the column is positive because of the easy downhill walk on the moment diagram. The shear in the beam is negative because of the tough uphill walk along the bending moment diagram of the beam. The shear force diagram in column CD is composed of 2 parts. One is from the triangular portion of the bending moment diagram, if we split it into basic parts. Another contribution is from the parabolic portion of the bending moment diagram. We have considered this in another video, and we can assume that the bending moment diagram and shear force diagram for simply supported beams and cantilevers, such as this one from C to D, are either available on a formula sheet or memorized. That means the shear force at C is the shear force at the base of a cantilever, namely Q times L, which gives the value 12 kN. Let us now take the step from the shear force diagram to the axial force diagram. For that purpose, draw the shear forces implied by the shear force diagram onto the end of each member. Notice here that the members are pulled away from the joints. That is because we'll soon consider joint equilibrium, which is what we have referred to as equilibrium at a point in an earlier video in this short course on equilibrium. Do you see how the positive clockwise 12 kN shear force in column AB gives this end force? Do you see how the negative counterclockwise shear force in the beam gives these arrows? Similarly, here is the 12 kN negative shear force at the top of column CD. The black arrows in this figure represent the equal and opposite forces acting on the joints. This transfer of forces from the member ends to the joint is a reflection of Newton's third law, as we saw in an earlier video. The important point now is to observe that this 4.8 kN force is pulling point B upwards, meaning that column AB is in tension. That is reflected in this plus sign, and confirmed by the earlier observation that the foundation at point A is in tension. The two 12 kN arrows are pulling at either side of the beam, meaning that the beam is in tension. That is reflected in this plus sign. Finally, the downwards pushing 4.8 kN force at point C means that column CD is in compression. That is reflected in this minus sign, and confirmed by the earlier observation that the foundation at point D is in compression. Thanks for watching this video. Please visit terje.civil.ubc.ca Toolbox for more videos and more material relevant for the modern structural engineer. See you soon.